Hi everybody, me again. Are you sick of me yet? All right, we're in the middle of chapter 10, which is radicals. We're going to learn more about properties of radicals and simplifying them. This homework, again, I'm going to do as much as I can in here. These are all so different that I might have to do almost every one of them again. So hopefully this is helping you though, so that when you do get stuck in your own homework that you can go back to something and take a look at what you have to do. So I'm really hoping it's a good resource for those of you that are using these videos. So, okay, so let's start. As a review, we have the product rule, which applies to radicals. So, if you have two things multiplied underneath a radical sign, you can split them into two separate pieces, and this is multiplication. So this is, square root of x times square root of y. These are equivalent. But if we go the other way, okay, so if we're going to say if we have two separate ones and then we're going to bring them together, the radicands don't have to necessarily be the same, but the indexes do right here. So these numbers in here have to be the same. So for instance, I couldn't combine the square root of x times the cube root of x because I've got an index of 2 here, even though it's not written. So those can't be combined. They have to have the same index for this to work. Okay? So, I mean, even just like the one up there, the square root of 7 is not, here, let's look at this. The square root of 7 isn't a perfect number. Okay? But when I combine them through this property, they become perfect. So if I take the square root of 7 times the square root of 7, I'm using this going that way. Okay, so I can say that's the same as 7 times 7, which is the square root of 49, which is 7. Okay? So anytime that you have numbers in here, I want you to check these with a calculator. So the square root of 7 times the square root of 7 will give us 7. Okay, so on a test situation, make sure that you check these with a calculator where you can. And there's a lot of them you can't once we start throwing letters in there. So, all right, cube roots. Well, what about cube roots? Same thing. We have the index here is equivalent. So we have the cube root of 7 times the cube root of 49. Now, as a cube root, these are not perfect cubes, but together they could be. 7 times 49. I mean, I have no idea. So I'm going to take, why did I hit that? No, I want math. I want to take my cube root, which is number 4, okay? And I want to take the cube root of this product and see if it comes out nice and neat, which it is. So 7 times 7 times 7 is whatever this product is. Okay? So that'll just be it. And you can just put a 7 in there. So, sorry, I didn't check the other one. That should have been a 7 as well. All right. Okay, so this is the product rule for radicals, and we also have the quotient rule for radicals. And I know I've already said these, but the same thing goes for division. So I can split if I want to, but if I'm going from this to this, these two indexes need to be the same in order to combine them underneath one radical. So you just have to be careful about that. So for instance, the one that we have up there, you can split it. Okay, so each piece, each numerator and denominator can get its own radical sign, and then these are perfect squares. 8 times 8 is 64, and 9 times 9 is 81. So we have 8 ninths. So let's make sure that that's true. So we will take the square root of 64 divided by 81. And we'll turn that into a fraction, 8 ninths. Okay? All right, so these start out pretty easily. And here it truly, it doesn't matter how many you have. I mean, this is not limited to just to two things. This is not limited to any amount. So we could do 2 or 3 or 5 or whatever. So here we could say, you know, we've got, to bring these all together, we've got 5 times 25 times 1 over 3 times 3 times 3, and we want the cube root of that. This is just one way of doing it. 5 times 25 is 125. 3 times 3 times 3 is 27. Then I can split cube root of 125. Because alone those are not perfect cubes, but together they are. 27. See how now I'm going to give each one its own radical, but they have to be cube roots, because that's what I started out with. Cube root of 125 is 5, I believe. Yes. Well, let's just make sure. Cube root of 125. 5 times 5 times 5, I believe it is. Yeah. And the cube root of 27 is 3. So this would be 5/3. Okay. So if this was a test question, we would want to check that. So you would want to take the cube root of 5/3. No, we'll get to put the 3 in there, Simone. Okay. Times the cube root of 25/3 times the cube root of 1/3. Oh. And then we would want to change it over to fraction notation to check 5/3. Perfect. Okay? So check these both ways. You know, do it by hand, check with a calculator. That's really ideal. All right. Now this one, first of all, let's just, without rewriting the whole problem, let's just split it first of all. Okay. So I'm going to give each one its own cube root sign. And the cube root of 3 is just really the cube root of 3. There's nothing that we can do with that. Okay? And to check that out, we're going to say, all right, well, let's just try the cube root of 3. So we're going to take the cube root of 3 and see, does it come out to be a nasty decimal? Yeah, then we're done with it. Okay? And the cube root of 64, I believe, is 4. Isn't 4 times 4 times 4 64? I shouldn't really say if I don't know for sure. Yes, it is. It's 4. So this is as done as we can get it. Okay? This stays the way it is, and this one can be reduced. So for these, you're going to want to probably put in a fraction first. And on the top, we have the cube root. So we don't want this one. That's the square root. We want to do this one first. So we're going to fill in the cube root of 3 and then a 4 underneath there like that. Okay? All right. Same thing here. Now we're starting to deal with our letters. Our variables are coming into play here. So we have this. Now I have both multiplication and division. So since I have the same indexes here of 2's, I can combine everything. So x times x is x squared. And 3 times 48, hopefully, is a perfect square. It's 144. Then we can split it. So we've got this one and this one. Now the square root of a square is itself, so that's just x. And the square root of 144 is 12. Okay, so we can check that piece of it on the calculator. But we can't check this piece. So we have x over 12 for our answer. All right, so now we're going to go the other way. Separately, these things don't do anything. I can't take the square root of 45. Again, I can always check that and do the square root of 45 and go, yeah, that's something that I don't want to mess with. So my only other choice right now is to throw them underneath one radical, right? Because I'm using the rule in reverse, which is fine. And 45 divided by 5 is 9, correct? So we take 45 divided by 5 and we get the square root of 9, and that is equivalent to 3. So we can check it this way. Square root of 45 divided by the square root of 5 is 3. Okay? This is really good practice though, because when we get into this kind of a situation, we can't use that calculator to check it. So so it's really good practice to do the ones with numbers by hand too. So this one's the same thing. I'll let you be on that one. Okay, so this one's different. Okay, so let's first of all take a look at, oops, what did I do that for? Let's look at 48 as a cube root. Okay, so that's not perfect. Can't come out nice and neat, and we can never express in decimal form. So now what do we do? Well, what I'm going to suggest that you do is start to make a chart, okay? And I have made one here for myself, so I want you guys to think about, you know, doing some sort of a chart like this. I want all my, okay, so I'm going to make a chart here. This is hard. It was really easy on my paper. Okay, and I'm just going to go up to 2, 3, 4, 5, and 6. Let's just do that. Okay, I want all my perfect squares here. So I want to do 2 times 2, 3 times 3, 4 times 4. So these are all my perfect squares here. 5 times 5 and 6 times 6. And on and on and on. I mean, I encourage you to do more of these. I went up to 10 on my 2's. Now I'm going to do my perfect cubes, which is going to benefit me over here because I've got cube roots up in here. But that's not working very well right here. Okay, so now I'm going to do my 2's again, but I'm going to do it 3 times. So 2 times 2 times 2. So I've got 8. 3 times 3 times 3, which is 27. 4 times 4 times 4, which is 64. My 5's turn out to be 125. My 6's turn out to be 216, and on and on and on. Taking this number and multiplied this many times. And then I'll do it for my 4's and 5's. I'm not going to do very many of these because these get large very fast and we don't need very many of them. I've already calculated these out, so you can, you know, do however many you like. I mean, there's no way we're going to get into 3,000s. We're probably not even going to get in the 200s. So these are probably the only 2 that we'll ever need. And then the 5's, we might only use the 1, which is 32, just because the numbers, we usually don't deal with numbers this large. But I'm going to write them down anyway so that you can kind of see what I'm doing here. So this chart tells me my perfect squares, my perfect cubes, my perfect fourths, my perfect fifths. All right, and that's going to really help me. So when I'm looking at a 48, I'm going to say to myself, well, 48 is not perfect, but is there one of these numbers in that 48 that is perfect? Because when I simplify, I have to take out all the perfect thirds that there are. I can't leave them underneath the radical sign. That's just a rule. I have to take them out. Okay? So I'm going to say, well, let's see. 48 divided by, obviously 64 is too big, so let's try 27. We always want to go backwards. Is that perfect? No, it's not. So let's do 48 divided by 8. Does that work? Yeah, 6. Okay? So what I'm doing is I'm taking these numbers and I'm dividing them into this number here. Okay? So I'm going to rewrite this problem. Now I've got my cube. I've got a negative 48 x8. And I'm going to rewrite this. I'm going to break this apart into something different. All right? I'm going to choose to break this into a negative 8 times a 6. Isn't that negative 48? And then I'm going to choose to break it again, this piece of it, and I'm going to say I'm going to choose to do this. Now, why did I choose to do that? Well, because I've got my perfect cube here, okay? 8's on my list. And any power that's divisible by 3 is perfect. Because remember my rule that the third root of x to the 6th exponentially is x to the 6/3, which is x squared. See how nice and neat it comes out? So what I want to do is I want to do multiples of 3 because I've got a 3 here. I've got 2 left over. Remember, when I multiply, I add my exponents. So this would be 8 x's. Now what I want to do is I want to split it into 2 different radicals. I want to do my perfect, this one and this one, over on this pile. And I want to keep my non-perfect over here. So I'm separating them. I'm separating my perfect cubes from my non-perfect cubes. Now these all can come out because the cube root of negative 8 is negative 2. Now if you don't know that, besides your chart and the negatives messing you up, we will do the, why do I always hit that first? I'm not sure why I'm doing that. Negative 8. We get negative 2. And I did this one for you right over here. Okay, so we're going to take 6 divided by 3 for 2 of them. Okay. And then this has to stay in because the cube root of 6 is a messy decimal. And this number is below this. I can't do groups of 3 if I only have 2 of them. Okay, so you can look at this as how many groups of 3 can I get out of 6? I can get 2. So there's your answer. Oops. That's a common mistake too. Yikes. To forget that. So minus 2x squared, and we want to take it multiplied by the cube root of 6x squared. Well done. All right. So you can't leave any perfect cubes behind underneath this for a final answer. There can't be a perfect cube sitting inside here. So we're going to be doing a lot of these. You'll get used to these if that was a little fast. This chart's really going to help. Okay, so now we're into our fourths. So we have the fourth root of 81 x4y. Look at this. 81 is a perfect fourth. It's 3 times 3 times 3 times 3. See how that works? These are my fourths. And then this would be 3 to the fourth. So I'm going to split these into my perfect fourths and my not perfect fourths. I don't have to break this apart because it's perfect. Any multiple of 4 is perfect, so I'm going to leave that one alone. This one has a 1 on it, and I can't do anything with that, so I just throw it in that pile. This is my bad pile, this is my good pile. So now these can come out. The fourth root of 81 is, we just saw that, is 3. The fourth root of x to the fourth is x. And then we have the fourth root of y left over. This is not perfect and can't ever be. Okay? So here we would type in 3x, then we want this as a fourth root of y. We should probably check these just to be sure. Okay. All right, what do we have here? We have combining these, okay? We have 2 of them. So I'm going to choose to throw them all underneath 1. So 5 times 10 is 50. X is left there, y squared is left there. These powers are underneath that, so these can't be done, nothing can be done with that. Now, is there a perfect fourth within a 50? No, because 50 cannot be divided by 16 evenly. So this one's done. There's nothing I can do with that. I can't pull a perfect fourth out of there. And these can't be turned into perfect fourths, so we're finished. Okay, so we have the fourth root of 50x y to the second power. And that'll be done. All right. I'll let you be on that. Oh, no, this is one of those really weird ones. Okay, I better do this one. So pay attention to this one because this one's different, even though it doesn't look different. At least it wasn't in my preview one. So we have 2z times fourth root of 8z. So we can combine those into fourth root of 2 times 8 for 16, z times z for z squared. Now back to my chart, I'm going to look for perfect fourths, and 16 is one of them. 2 times 2 times 2 times 2. Okay, and then this one's not perfect because I'm underneath the 4. I can't make 4 groups of z's with only 2 of them. So I'm going to resplit this into 16, and then I've got z squared. Okay. This is 2. And it looks like I'm done. But I'll guarantee you that it's not right. Okay, so let's put our answer in here just to see. But we're gonna get an error message on this. And then you have to ask yourself, why? Why is that not right? I did everything the way I did it last time, but this time it's not right. Well, this is one of those really weird problems where if I were to turn this into an exponential, this piece of it, and analyze it, it can be reduced further. So I've got my 2, that's this one over here, and I'm going to turn this into z to the 2/4. Look at that. 2/4 as a fraction can be reduced down to 1/2. Okay? So this is the same as, you know, I'm going to actually put them all in here. This is your power. This is your index. This and this are not needed because they're assumed to be there. So that's what we want. We want 2 times the square root of z. Because the fourth root of anything squared is the same as the square root. So we want to just clear that out of there. Let's check for equivalency here. And that's right. And I think I've only assigned one of those. But just beware. I mean, I might have something like that on a quiz or a test. Always double check these 2 values right here to see, gosh, could those possibly be reduced further? Is that reducible? Is 2/4 reducible? Yeah. Let's look to see what we had over here. We had 1/4. That's not reducible. We had 2/3. See how those are not reducible? What else did we have? Not much. Okay, so we're going to have to check for that. All right. Okay, so now we have addition, subtraction, and anytime that we have addition, subtraction, the rules change. Okay? So I'm going to choose to look at this as one piece and one piece here. I'm going to put them in parentheses to show that this is one like an X and this is like a Y. Okay? So what I can do is I can use my product rule to do this and to say X times Y underneath 1. Now I'm going to FOIL. Okay, so we're going to do first X times X. Outside, negative 6X. Inside, positive 6X. Last, minus 36. Now I'm going to combine like terms. I've got a negative 6x and a positive 6x, so those are gone. So I have x squared minus 36. And this is not equal to this. Those are not the same. Because look at what my rule is up here, way up here. My rule is only for multiplication. This is xy. That means x times y. There is no rule that says x plus y is something. Okay? So when I first chose to say it's x times y, or this times this, then I can combine them underneath 1 and mess with it. But now I can't anymore. I've got to leave it alone. So it's got to be this one here. All right? Let's try that. So we have the square root of x squared minus 36. Perfect. Okay? Same thing here. Okay? Now you're dealing with cubes, but it doesn't really matter. Well, we should probably do this one, huh? Well, I'll get you started anyway. So I can throw this all underneath one cube root sign. Okay, and now I'm going to take this a and I'm going to multiply it through 3 times. Then I'm going to take this 6 and do it again 3 times. I'm going to combine my like terms, and I think there's a bunch of terms that are going to drop, and then you're going to end up with whatever. But you can't take it out of the radical. Okay? So that one's very, very similar to what we got here. So I'm going to erase all of this, but you guys need to write down that chart of perfect 2s, 3s, and 4s, and 5s. I think this only goes up to 5s. Okay. So I might have to write these down again. 2, 3, 4, 5, and 6. So I had, just as one column, I'll just do these as I need to. I had 4, 9, 16, 25, 36. Okay. And on and on and on. I mean, this goes on for a really long time. Okay, so I'm going to take a look at 175. And the first thing that I'm going to check for is to see if it's a perfect square in and of itself. Boy, it's hard to say. In and of itself. Is 175 perfect? Nope, it's not. I can't have a decimal answer, okay? I have to have an exact answer, right? Using my radicals. But I bet there's a perfect piece within there. Is one of these numbers here, so I'm keeping this at the bottom here so that I can, I'm going to do my 3s and my 4s and my 5s as I need to. I'm going to look to see, is there a perfect piece within it? Well, I'm pretty sure there's a 25 in 175, isn't there? 175 divided by 25 is 7. So I'm going to choose to rewrite this as 25 times 7, because that's 175. I'm just going to choose to break it apart. And then I'm going to split it. So each one gets its own square root sign. And then this one is perfect, so it can come out. Square root of 25 is 5. So I've got 5 roots of 7. Okay? So now what I'm going to do for checking, before, let's just say this isn't a test situation, I'm going to take the square root of 175, get an answer, some decimal, which I already did. I should have just seen it up there. And then I'm going to take my equivalency, which is 5 times the square root of 7, and see if it's exactly the same number. See how theirs are exactly the same? So this is equal to that. So what I'm looking for is, when I'm done, I can't have a perfect square root sitting underneath here. Okay? 7 is not on my list here. I can't have one of these numbers sitting inside of the number that's here, hidden within multiplication. So I'm done. So I've got 5 roots of 7. Okay? So you're going to try to pull those perfect pieces out of there. So now this is where the fifth column is really going to come in handy. So we've got, just to write these down, we've got 32, we've got 243, and dot, dot, dot. I don't really need those. So the first thing that you're going to want to do is you're going to check to see if 160 is a perfect fifth. You do 5 first, then you do math 5, then you do 160, and it's not. So now I have to say, well, is there a number within it? Well, it can't be this one because it's over. So I'm going to see if 160 is divisible by 32. Okay? To see if there's a 32 hiding within it, and there is. It's in there. So what I'm going to do is I'm going to rewrite this as the fifth root of 160. I'm going to choose to rewrite it as 32 times 5 because I'm trying to pull the perfect fifth out. Then I split 5 times 5. This is perfect. Okay, I go back to my chart. The fifth root of 32 is 2. So I have 2 times the fifth root of 5. And this is not perfect, so I'm done there. Okay? So let's check for equivalency. We've got the fifth root of 160 here. 2 times 5, 5, 5. Yep, they're exactly the same. So 2 times the fifth root of 5 is 2.759, blah, 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 but so is the fifth root of 160. So we're done. So that's how you would check those. Please check those before you submit your homework. Not so much your homework, but your, well, yeah, your homework too, but your quizzes and tests for sure. All right, so now we're going to start working with some variables. I think I'm down at the bottom here, so I'm going to move up to the top, and I'll come back to that chart. So I've got the square root of 12a squared b to the fifth. All right, 12 is not perfect. So I'm going to look at my chart to see what's the biggest perfect square sitting and hiding within a 12? Well, it's a 4, correct? So I'm going to choose to rewrite my 12 as 4 times 3. Okay, 6 times 2 is also 12, but neither 6 or 2 are perfect, so that doesn't do me any good. This has to be divisible by 2, and it is, so that one's a perfect variable. 5 halves is not perfect, because 5, that's 2.5. I can't have that. So I'm going to choose to drop this down to the next closest number that's divisible by 2, which is a 4. And then I would have 1 left over, because I have to always check to make sure that this is the same as all of this. So 4 times 3 is 12, got my a squared. B to the fourth times b to the first is b to the fifth. So I've just rewritten it. Now I can use my product rule and I can split. And I can stack my perfect, perfect, and perfect over here. Those are all going to come out, right? And then my not perfect and not perfect over here. So the square root of 4 is 2. The square root of a squared, remember I'm doing 2 divided by 2 for 1. B, it's 4 divided by 2 for 2. And then I've got this. So I'm completely finished. So let's check her. This one is not checkable on a calculator, so that's why I'm kind of harping at you guys to not use it, but just to use it as a check, because then you get to these where you can't and you haven't had enough practice. So we do need to do them both ways. All right, holy moly, what do we got here? I'm going to leave you alone on this one. Same concept. You want to split. You want to take the perfect cube out of there. Well, let's take I'll get you started. I don't even have my cubes on there. Okay, so you guys figure out what is the biggest perfect cube within a 48. Biggest. It's got to be the biggest. 64, 125, 216. Let me just finish this chart here so that we're done. I should have just copied it over. If I was smarter than the average bear, I could have figured that one out, but I'm not. Is it 8? I think it's an 8. So we're going to split this. Okay? So I've got the cube root of negative 48, x4, y5. I'm doing groups of 3s. Okay, so I have to split this into, and I'm just going to do this piece of it for you. We've got negative 8 times 6. You always want to drag that negative on the outside. Okay, so I'm going to split this into groups of 3. Well, the biggest group of 3 that I can get out of 4 is 3, right? And I would have 1 left over. And the biggest group of 3s that I can get out of here is also 3. And I would have 2 left over. So now you're going to split. Now, so now you're going to do this. You're going to group them. Perfect, perfect, perfect. And then you're going to take what's left. Not perfect, not perfect, and not perfect. Okay? So that one should be fairly good to go. Now this one's not. This one's a little different. All right. So I can combine these because they're both fourths. So I'm going to stick it all underneath one radical sign. So I've got R8, 5t. Okay? Everything's multiplied. 2 times t to the 5th times 8 times r divided by 8 r to the 8th times 5 times t. Now within this, I can start simplifying. I'm going to use my radical or my exponential rules that I've learned from last time. So what do I have here? I have t to the 5th. I'm going to put my, sorry, I'm going to put my ones here, divided by t to the 1st. So I've got t to the 5th divided by t to the 1st. Remember, when I divide, I subtract. So this is t to the 4th. Okay, so I've got t to the 4th. So I got rid of my t's. Now I've got the same thing here, r to the 1st and r to the 8th. r to the 1st and r to the 8th. Again, I've got division, so I'm subtracting. 1 minus, no, that's an 8. 1 minus 8 is r to the minus 7, which is 1 over r to the 7th. Okay, so that's where we're going to go with the r's down here. They have to stay underneath. The bigger number is below. So I got my r's done, I got my t's done. I can't do anything with this, the numbers, so I'm going to do 2 times 8 for 16. And then I've got the 5 underneath there. So I can reduce this down first if I choose. All right, now what do I got going on here? I don't know. Let's split it. This whole numerator looks perfect to me. 16 is a perfect fourth, right? 16 is a perfect fourth. It's 2 times 2 times 2 times 2. And anything divisible by 4 is perfect, so that's going to come out as a t. I can do one group of 4 out of 4. And then this stuff on the bottom doesn't look perfect. This is not perfect, and this is, well, this one I can split though. I can get groups of 4 out of that. Yikes. So here I have the 4th root of 16 is 4. The 4th root of t to the 4th is t. And here I'm going to choose to rewrite that as, I'll just do it over here, 5. Okay, I'm going to take 4 out, and there would be 3 left over. So when I re-add those, I get 7. So this has to stay in there, and this one can come out. So they're really, the r to the 4th root, is the perfect piece. So I'm going to separate that. And I'm going to leave this in because those are not, and I'm underneath here. So this comes out as an r, and then that has to stay in there for 5r cubed. Okay? Oh, sorry, 4th root. I always forget to do that. I bet you guys are doing that too. It's really hard. So we have 4t over r times the 4th root of 5r cubed. Yikes. Oh, we should probably check that one just to make sure. I could have done something incorrect along the way. Pretty easy to do that. So I'm just going to get this in here. Fourth root. Are you kind of watching how I'm doing this in here in case you're having trouble entering? Ah, what did I do wrong? Oh, this is a 2. Why did I put a 4 there? I don't know. The fourth root of 16 is 2, not 4, Simone. I even said that, and then I put a 4 there. Quick and easy fix, okay? So this is how you have to enter it in. Well, you have to enter it in correctly, obviously. All right, this is going to be a long lecture here. I think I can let you be on that one. You know, you're going to do the same thing. You're doing groups of 7. All right, well, maybe I should do this one. We haven't done 7s yet. I don't want anyone to start panicking. Ah, she left us alone on a 7th root. How could she? Yeah, I know. It's called laziness. All right, so within this 7th root, I can't do anything with my x and my y because those are different letters. But I can see if this is reducible. So I'm just going to randomly choose to, not randomly, but I'm just going to put this into fractional form and see what that is. That's 3/128. Okay, that is not reducible. Okay, so that's my first check to see if I couldn't reduce 3/128. Now I know 3 can't possibly be a perfect 7th, but this one could be. So I'm going to check that just alone as just a perfect 7th. So I'm going to hit 7 and then 128. Whoops. What the heck happened there? 7. What did I hit? I don't know, but I did not hit with the right button. So that is a perfect 7th. So if I take 2 raised to the 7th power, or take 2 multiplied by itself 7 times, I get 128. So that at least is the perfect piece. Okay? So I'm going to, well, I haven't done anything here, so I'm just going to, I was checking for equivalency here. Okay. Now I can't make this 1 into a, I can't get 7 groups out of 1, but I can get 7 groups out of 35. Okay? So what I'm going to do is I'm going to split it this way, because this whole numerator is not perfect. And this entire denominator is y35. So this entire numerator stays the same. And this is a 2. We just found that out through the calculator. And 35 divided by 7 is 5. And we're done. You're not going to make me check all of these, are you? I think this one I might. These are square roots, so these are a little easier. All right, so try that one. Okay. What is 27 times 3? 27 times 3, is that a nice 81? Nice piece of cake. Okay, then these are different. These I certainly cannot leave you alone on. But I think I'm going to erase first. So how you doing? Are you hanging in there? I sure hope so. I hate it that you guys can't talk to me. This is just craziness. I don't like it. Are you yelling at your screen right now? All right. Remember this? We're going to need that. So the square root of 12 times the cube root of 12 cannot be combined. I have a 2 here and a 3 there. I cannot combine them into 1. So the product rule does not work. So you look at it and you just go, well, now what? Right? Well, we'll use this rule and see what we can do. I'm going to put my 1 here and my 1 here and my 2 here just to remind myself what's going on. So here I have 12 to the 1/2 power. And here I have 12 to the 1/3 power. Well, my exponential rules say that if my base is the same, I can combine. And I do have a like base of 12. And I combine by adding 1/2 plus 1/3. Just like if this was an x. All right. I have a common denominator of 6. So I've got 3/6. I'll just do this one by hand. Plus 2/6. Now, if you don't like doing that, use your calculator, okay? So this is 12 to the 5/6, right? So if we didn't want to do it like that, we could do 1/2 plus 1/3. Fraction, enter, 5/6, okay? And now I'm going to go back from this to this because it's going to want it in radical form. So that's the same as 12 to the 5th power to the 6th root. Let's try that. So we have the 6th root of 12 raised to the 5th power, and I don't think, yeah, I don't want this, don't make that into a number. 12 to the 5th, just leave it. Okay? So here we might have to start messing with it to get it combined. We combine them exponentially, not radically, because they're not combinable as radicals, but they sure are as exponents. So that's what we'll have to do there. Same thing here. But the problem here, it appears, first of all, I have different indexes, but I also have different numbers underneath there. Okay, see here I had a 12ths. So exponentially they can be combined. Here I don't. I would have 27 to the 1/5 power times 9 to the 1/3 power, and I can't multiply those. Okay? Oh, you know what? Oh, I'll go back. I wanted to check this one for equivalency in the calculator to show you. All right, well, let's just do that right now real quick. Sorry. Okay, I originally had the square root of 12, just because these are numbers and you can, times the, I almost did it again, 3rd root of 12, get a decimal equivalency. And now I'm going to check it with this. I want the 6th root of 12 raised to the 5th power. And it's exactly the same. So before you would hit submit again, check. And this one as well. We're going to check this one. See, now you can't do this in a calculator, but you can only check these in a calculator. I mean, your calculator would never be able to give you this form. Okay? All right. So what do I do? Well, let's see. Let's use our ingenuity here. I know 27. I just recognize 27 as 3s. 3 times 3 times 3. I recognize 9 as 3 times 3. So I'm going to rewrite this as 3 cubed. That's 27. And is that a 3? That's a 3. Okay, and 3 squared. All I've done is I've rewritten 27 as 3 cubed and 9 as 3 squared. Do you see now how I have the same base? I'm trying to make that base the same. So now I'm going to change that into an exponential. I've got 3 to the 3/5 power times 3, another base, to the 2/3 power. Now my base is the same, and I'm going to do like what I did up in here, and I'm going to add my exponents, because when I multiply with the same base, yikes, that was a 3, I add. Let's see what we got here. We have 3 divided by 5 plus 2 divided by 3, and that is 19/15. Whoop. So now I'm going to go back into my radical form and say that that is 3 raised to the 19th power 15th root. Now I'm not done. Think about why I'm not done. Why is that not done? Well, because I'm looking for groups of 15 and I've got 19 to pick from. So this number always has to be less than that number for you to be done. Look at it, see how that one's less than this one? I can't get 6 groups out of 5 things, but I can get 15 groups out of 19 things. So I'm going to choose to split this into 3. I'm going to take 15 of them over here, and I'm going to have 4 left over, aren't I? Because 15 plus 4 is 19. This is 3. I've got 3 groups of 15 and I have to have, I have 1 group of 15. And I'm finished. So make sure that that's completely and totally simplified. So first of all, let's just check. Let's just check to see that this is not correct. Okay? So I'm just gonna show you a couple things here, and then we'll check for equivalency. So this one probably says no. No, although your answer is equal, it's not right because it's not completely simplified. So we're going to go down to this one here. Try that one. 3. We want the 15th root of 3 raised to the 4th power. It likes that one better. And now we're going to check for equivalency. So we want to do the 5th root. Obviously, it is right, but we want to check this in a test situation. The 5th root of 27 times the cube root of 9. Now I'm going to check this one. I've got 3 times the 15th root of 3 to the 4th power. Well, bam, same number. Okay? Now, if it didn't come out to be exactly the same, then I'm going to want to go back. I'm going to want to start retracing my steps to see, okay, what did I do wrong? Where did I go wrong? That kind of stuff. Okay? Ooh, I've got 2 more. I'm going to be underneath an hour here. Same thing here. I'm not going to do this one. X to the 4/5, x to the 3/4. I've got the same base. Add and change it back. And see if you have to reduce further. If this number is bigger than this number, you're going to have to keep going. If not, you're done. And this is a really easy word problem, but we'll still do it. It says the car's speed and the skid mark it leaves behind when you slam on the brakes are correlated. So here it's saying that the speed is the square root of 9 times the square root of m, 9 times the square root of 9 times m, excuse me. Where this is your speed, again you have to label what you have, and m is your skid mark. Okay? The first thing it's asking us to do is to simplify. Well, what can I do to simplify? Well, I can see that I've got a perfect piece and a not perfect piece. This comes out as a 3. That has to stay in. Okay, that's the only thing I can do with this. Now, this has to be, crazy as it sounds, this has to be a capital M. If you do it with a small m, it says it's not right. So don't do that, because this is a capital M. How do I know that? Because I put a small m in there in the beginning and then it said it was wrong. So I've already made that mistake. All right, so now we want to know the speed of the car at 64. The skid marks are 64 feet long, so we want to know the speed of the car. So look at how easy it is to put it into this formula. Like if I put it in here, I would do 9 times 64. I get this big ugly number that I don't know what to do with. But this one I can really see it because I don't even need the calculator. 3 times the square root of 64. Well, square root of 64 is 8. 8 times 3 is 24. So it's got to be 24 miles an hour. Okay? But I could have used the calculator as well and did 9 times 64. So So let's just do that, just to prove that we can. 9 times 64, still 24. Okay? Alrighty, that's 10.3. I will do one more, 10.4, and then we're done with chapter 10. So I'll see you on the next one. Take care.